Hello there. Today I'm going to show you why is the gravitational potential energy always negative. So you will find this a bit absurd, that how can the gravitational potential energy be negative? I mean, how will you define it? So whenever potential energy is negative, that will that can be defined as you will require positive you will you need to do positive work to bring it to the zero position. So zero position means that the point where the potential energy is zero. Okay, so uh, we are free to choose what will be the zero of our potential energy. So for our convenience, to get all the calculations working, we take infinity as the zero of our potential energy. So that means that infinity, the potential energy of any object, suppose in this case we take the mass m separated by a distance of infinity from this capital M. So this is a bigger mass, of course, and this is a capital M, and the potential energy at infinite distance of m equals to 0. So as you can see, there will be a force exerted, or there will be a gravitational force exerted on this small m by this mass over here, and that force we are gonna assume that it will be negative, since there's another force acting in the opposite direction. So we're gonna assume that this force, the force external, is positive, and the force, so these are vectors, okay, and the force exerted by gravity, I'm sorry, is negative. Okay, so what does this mean is these are equal in magnitude. Okay, these are equal in magnitude, that is F equals G, F external, the external force is Gmm upon r squared. And since these are equal in magnitude but in opposite direction, the force of gravity will be minus Gmm upon r squared, since they are opposite direction. Okay, so we got this. So I want to find out that what will be the work required by what will be the work done by the external force to bring the point from infinity to r, from infinity to r. So we're gonna calculate, suppose so at each and every point, okay, at each and every point at r, the gravitational acceleration is changing. Okay, so at this point over here, the gravitational acceleration may be something. At this point it will be greater from that of this point, and at this point it would be way greater from this point. Okay, so at each and every point the gravitational acceleration is changing, and we're gonna assume that for a very small change dr, the gravitational acceleration is the same. Okay, so for very small change dr, the gravitational acceleration is the same. So we can calculate, so this will be the work done. Okay, from infinity to r will be the work done, but very small change in the work done from infinity to r gives us the force exerted by the external force. Okay, what did I just say? The external force times dr, that gives a very small change in the work done. Okay, that's a very small part of the work done. So if you were to integrate this, okay, that just means what will be the total work required, what will be the total work done by the external force for bringing the mass m from infinity to r. So if we integrate this, that will be from infinity to r, these are the limits. Okay, so that will be capital R. Okay, and I think I should write this as small r, since I've taken this point over here as capital R. So that will be force, that is external, times dr. Okay, so we are going to replace this force, that is the external force, by this value here. This is r. Okay, r squared. We are going to replace force that is external by this value. So if we replace it with this, we get it as the work done from infinity to r will be the integral from infinity to r, this capital R, of g mm upon r squared, sorry, I should do this small r squared times dr. So you might notice here this thing gmm, this gmm is constant, and the only thing that is changing is the distance. So this thing is changing. Okay, so we can also rewrite this as gmm multiplied by the integral from infinity to r of 1 upon r squared. So 1 upon r squared is the same thing as r power is to minus 2 times dr. Okay, r power is to minus 2. I hope this resembles r power is to minus 2. Okay, so if we by the inverse power rule, you get this as minus 1 upon r. Okay, so if you were to multiply, so we get this as gmm, we'll get this as minus 1 upon r, okay, multiplied by minus 1 upon r. The limits are infinity to r. So anything, so if you are going to replace this r with this capital R, I'm sorry, this should be capital all over here. So that's the point, and that's the point along the distance. Okay, that's the point, that's one point that is present in the distance. Okay, so if you were to replace this r with this r, that would just be minus 1 upon capital R. Minus 1 upon infinity gives us 0. Okay, so that will give us the work done by the external force is negative gmm upon r. Okay, this capital R over here. So that's just the point. Okay, this r is this point over here, and that's the distance, that how far is it from this mass, this capital M. Okay, so the work done by the external force. Okay, first let me tell you that the forces, the both gravitational and external forces, are opposite in direction, and the work done by the external force will be the opposite of work done by, will be the negative of the work done by the gravitational force. Okay, so we can write it as work done by external force will be the negative of the work done by the gravitational force. So we can rewrite this. We know what is the work done by the external force. That will be g negative gmm on r equals to the negative of the work done by gravitational force. This minus and minus cancels out, and we get the work done by the gravitational force equals to gmm upon r. So you might know about the work energy theorem, and it states that the change in kinetic energy I'm sorry, the change in kinetic energy equals to the work done. Okay, so the increase in kinetic energy equals to the work done, that is, the final kinetic energy is greater than the initial one. Okay, so when the kinetic energy increases, the potential energy decreases. We can also say this as the change in potential energy equals to the negative of the change in kinetic energy. And since the negative of the change in kinetic energy is the same thing as the work done, we add a negative sign to it, and that just becomes the negative work. Okay, so the change in potential energy equals to the negative work done by the force. So since we are talking about the gravitational force over here, the work done by the gravity, okay, work done by the gravity, we know what is the work done by gravity over here, that's gmm upon r, will be the negative of the change in potential energy. Okay, and the negative of the change in potential energy. Okay, so we just take the minus sign from here to here and we get minus work done by gravity equals to the change in potential energy. So what does this change in potential energy means? It means that what is the change in potential energy? Okay, what's the change in potential energy as the mass moves from infinity to the point capital R? Okay, so that the final position is potential energy at R minus the potential energy at infinity. Okay, so that gives us the negative of the work done by gravity. Okay, so I'm running out of space over here, so I'm going to continue it over here. So we know what is the work done by the gravity and we know what is the potential energy at infinity, so we are going to substitute this by 0. Okay, and the work done by gravity, that is this value here. Okay, gmm upon r. So work done by gravity is gmm upon r. Okay, and negative of this means negative gmm upon r equals to the final potential energy, since final potential energy is the potential energy at this point r minus 0. Minus 0 gives us the same thing as potential energy at r. So this gives us, so we can deduce that potential energy at r will be negative, or will be the negative of the work done by the force of gravity. So this also means that if you were to so it means that the potential energy at r, that means the object has this much capability, this much, that it can do that much work in the negative direction or towards the direction of the capital M, the mass denoted by capital M. So it means that this M over here can do this much work. Okay, or can do this much work in this direction. The magnitude can do the magnitude of that much work in this direction or along the direction of the force of gravity. And if we were to bring this object to infinity, we would require the same work but in positive. So the amount of work required to bring this object to infinity, we would require this much work but positive. So that will be gmm upon r. So this will be the work I'm sorry, this will be the work required to bring the mass m from r to infinity. That's it, guys. So this is how the potential energy, so this is how we prove that the potential energy at any point, the gravitational potential energy I mean, at any point is negative, that is minus gmm upon r. So hope you like this video. If you like it, then please share, like, share and subscribe. Thank you for watching.